Hello, my name is Benjamin Mell, Regional Sales Manager for Gallagher Fluid Seals. This is part 2 of our ongoing video series on the basics of O-rings. In this video, we are going to introduce the concept of elastomers and their use as O-ring materials. An overview of what an elastomer is will be followed by more detailed information on specific elastomers that are commonly used as O-ring materials. This video is going to focus on the following topics. If you want to start at the beginning, please watch Chapter 1 in this video series on O-ring basics. First, we are going to explain the basics of elastomers, the primary raw material for most O-rings. Next, we will take a deeper dive on the most common elastomers used as materials for O-rings. These include nitriles, FFKMs, Perfluoroelastomers, or FFKMs, silicones, EPDM, AFLAS, and polyacrylate. Within each one of these elastomer families, we will discuss specifics on temperature and chemical performance, as well as a summary of common areas of use for that material. An elastomer is either produced naturally as gum rubber on commercial rubber plantations or manufactured synthetically by the chemical industry. Today, more than 32 synthetic rubbers are known. Modern synthetic elastomers were developed during World War II as global shortages of natural rubber forced their development. Modern elastomer compounds generally contain 50 to 60% base polymer. The balance of the compound consists of various fillers, vulcanizing agents, and other chemical additives which modify and improve the basic physical properties of the base polymer. Elastomers used in producing O-rings and seals will provide reliable, leak-free function if fundamental design requirements are observed and are matched to the application. Though elastomer is synonymous with rubber, it is formally defined as a high molecular weight polymer that exhibits little plastic flow and a rapid recovery from an extending or compressing force. Cured or vulcanized rubber generally meets the following requirements in order to be called an elastomer. It must not break when stretched approximately 100%. After being held for 5 minutes at 100% stretch, it must retract to within 10% of its original length within 5 minutes of release. The first elastomer that we are going to review is nitrile. Also referred to as NBR or buna, this is the most popular class of O-ring elastomers and has broad resistance to chemicals and temperature. Nitrile rubber is the general term for acrylonitrile butadiene copolymer. The higher the acrylonitrile content, the better the resistance to oil and fuel. NBR has good mechanical properties when compared with other elastomers and high wear resistance. NBR is not resistant to weathering and ozone. Heat resistance for buna is good up to 212 degrees Fahrenheit, with shorter life expected at 250 degrees Fahrenheit. Cold flexibility for NBR is dependent on the individual compound and can vary between -30 degrees Fahrenheit and -70 degrees Fahrenheit. Nitrile chemical resistance is strong for the following categories but can vary by individual compound. Aliphatic hydrocarbons such as propane, butane, petroleum oil, mineral oil, and fuels. Hydraulic fluids, dilute acids, and water up to 212 degrees Fahrenheit. Nitrile-based elastomers are not compatible with the following. Fuels of high aromatic content. For flex fuels, a special compound must be used. Aromatic hydrocarbons such as benzene, or chlorinated hydrocarbons. Polar solvents like ketone, acetone, acetic acid, and ethylene ester. Strong acids, brake fluid with glycol base, ozone, weather, and atmospheric aging. Because of its popularity as an O-ring material and its strong performance across a wide range of applications, slight alterations of the basic nitrile elastomer have been developed to solve specific problems. Hydrogenated nitrile, or highly saturated nitrile, known as HNBR or HSN, is a subset of nitrile. HNBR is a synthetic polymer that results from the hydrogenation of nitrile rubber. This produces superior mechanical characteristics such as wear resistance, extrusion resistance, and elevated temperature properties while maintaining similar chemical resistance. Carboxylated nitrile, or XNBR, is a special type of nitrile polymer that exhibits enhanced tear and abrasion resistance. For this reason, XNBR-based materials are often specified for dynamic applications such as rod seals and rod wipers. Both HNBR and XNBR offer similar levels of chemical resistance and weaknesses to those outlined for traditional nitrile. The advantages are primarily mechanical in nature with a slight temperature increase. Key takeaways are the following. Nitrile is the most used O-ring material. It has good chemical and temperature resistivity at an economical price point. Nitrile is widely used across hydraulic and fuel dispensing applications. Next, we will discuss Chloroprene, which was the first synthetic rubber developed commercially and generally exhibits good ozone, aging, and chemical resistance. It has good mechanical properties over a wide temperature range. Chloroprene is sold under the trade name neoprene, which is a trademarked product for the base polymer from DuPont. Temperature properties range from minus 40 degrees Fahrenheit to 250 degrees Fahrenheit. Neoprene offers strong chemical resistance to the following: paraffin-based mineral oil with low DPI, also referred to as ASTM oil number 1, silicone oil and grease, water and water solvents at low temperatures, refrigerants, ammonia, and carbon dioxide. It also has improved ozone, weathering, and aging resistance compared with nitrile. Neoprene is not compatible with the following: naphthalene-based mineral oil such as IRM 902 and IRM 903 oils, and glycol-based brake fluids. Aromatic hydrocarbons such as benzene, chlorinated hydrocarbons, and polar solvents such as ketones, esters, and ethers. The bottom line is neoprene is the first synthetic elastomer developed. It is primarily used within refrigerant and environmental sealing applications. Next, we'll talk about fluorocarbon, or Viton, which has excellent resistance to high temperatures, synthetic hydraulic fluids, fuels, and many organic solvents and chemicals. Similar to neoprene, the term Viton is a trademark brand, and the technical term for the base elastomer is fluorocarbon, or FKM. Low temperature resistance is not favorable, and for static applications is limited to about minus 15 degrees Fahrenheit, although certain compounds are suitable down to minus 50 degrees Fahrenheit. Under dynamic conditions, the lowest service temperature is between 5 degrees Fahrenheit and 0 degrees Fahrenheit. FKM has excellent heat resistance up to 400 degrees Fahrenheit and higher temperatures with shorter duration. FKM has strong chemical resistance to the following: mineral oil and grease, ASTM oil number 1, and IRM 902 and 903 oils. Non-flammable hydraulic fluids, also known as HFD, silicone oil and grease, mineral and vegetable oil and grease. Bottom line, FKM materials have excellent temperature and chemical resistivity, and should be used within critical applications where other elastomers fail. FKM has a higher price point than NBR. FKM does have low temperature limitations. Specific FKM compounds are available that perform better at low temperatures, but not as well as other elastomers. Next, we will discuss perfluoroelastomers, also known as FFKMs, which currently offer the highest operating temperature range and the most comprehensive chemical compatibility of any widely available elastomer. FFKMs are ideal for use in critical applications like semiconductor chip manufacturing, turbine engines, and chemical processing equipment. DuPont Calres was the first of these materials developed and to this day remains the market leader and most common brand of FFKM materials used. Wide ranges of specific FFKM compounds have been developed to solve specific application challenges. These materials are used across a wide range of industries such as aerospace, semiconductor, oil and gas, and chemical processing. FFKMs have excellent heat resistance up to 620 degrees Fahrenheit and cold flexibility down to -15 degrees Fahrenheit. These numbers are compound specific and should be considered with your application needs. FFKM elastomers offer strong chemical resistance to the following: aliphatic and aromatic hydrocarbons, chlorinated hydrocarbons, polar solvents such as ketones, esters, and ethers, inorganic and organic acids, water and steam, and high vacuum with minimal loss in weight. FFKMs are not compatible with the following: fluorinated refrigerants such as R11, 12, 13, 113, and 114, and perfluorinated lubricants, or PFPEs. Key takeaways here are: FFKMs offer even higher temperature performance and chemical resistivity than FKMs. FFKMs offer the highest level of fluorine in the O-ring elastomer group. These parts come at an extremely high price point, and these materials do not perform well at low temperatures. Next is tetrafluoroethylene propylene, or AFLAS, which is a copolymer of tetrafluoroethylene, or TFE, and propylene. Its chemical resistance is excellent across a wide range of aggressive media. AFLAS offers heat resistance up to approximately 450 degrees Fahrenheit and cold flexibility down to approximately 15 degrees Fahrenheit. AFLAS is chemically compatible with the following: bases, phosphate esters, amines, engine oils, steam and hot water, and pulp and paper liquors. AFLAS is not compatible with the following: aromatic fuels, ketones, and chlorinated hydrocarbons. The bottom line is that AFLAS is a fluorinated elastomer. However, unlike traditional FKMs that perform well in acid applications, AFLAS is designed to handle base chemicals. AFLAS is used extensively within steam applications and has a higher temperature capability than EPDM. Next, ethylene propylene and ethylene propylene diene rubber are particularly useful when sealing phosphate ester hydraulic fluids and in brake systems that use fluids having a glycol base. These materials are widely used within the automotive industry and for any application with water or steam. EPDM offers good heat resistance up to 400 degrees Fahrenheit in water and or steam, and cold flexibility down to approximately -70 degrees Fahrenheit. EPDM performs well in the following areas: hot water and steam up to 400 degrees Fahrenheit, with special compounds up to 500 degrees. Glycol-based brake fluids, such as DOT3 and 4, and silicone-based brake fluids, such as DOT5. many organic and inorganic acids, cleaning agents, sodium and potassium alkalis, phosphate ester-based hydraulic fluids such as HFD-R, silicone oil and grease, many polar solvents such as alcohols, ketones, and esters, ozone, aging, and weather resistance. EPDM is not compatible with the following: mineral oil products such as oils, greases, and fuels. The key takeaways here are that EPDM performs very well within water and automotive brake fluid applications. Additionally, EPDM has extensive FDA and NSF certifications. EPDM should not be used within hydrocarbon applications like hydraulic fluid, as the material will swell and ultimately fail. Now we will discuss silicone, which has good ozone and weather resistance, as well as good insulating and physiologically neutral properties. However, silicone elastomers, as a group, have relatively low tensile strength and poor wear resistance. Silicone materials offer the widest range of temperature performance, but should be limited to static applications due to their fragility and tendency to tear. Silicone has excellent heat resistance up to approximately 400 degrees Fahrenheit, with special compounds up to 500 degrees Fahrenheit, and cold flexibility down to approximately minus 65 degrees Fahrenheit, with special compounds down to minus 175 degrees Fahrenheit. Silicone offers strong chemical resistance with the following: animal and vegetable oil and grease, high molecular weight chlorinated aromatic hydrocarbons, including flame-resistant insulators and coolant for transformers, moderate water resistance, diluted salt solutions, ozone, aging, and weather. Silicone is not compatible with the following: superheated water steam over 250 degrees Fahrenheit, acids and alkalis, low molecular weight chlorinated hydrocarbons such as trichloroethylene, hydrocarbon-based fuels, aromatic hydrocarbons such as benzene and toluene, and low molecular weight silicone oils. The bottom line is that silicone has very strong high and low temperature performance. Silicone is used extensively in life science applications. FDA and USB Class 6 certifications are available in a range of silicone compounds. Silicone offers poor mechanical properties and should not be considered for dynamic applications. An extension of traditional silicone elastomers is fluorosilicone, or FVMQ. The mechanical and physical properties are very similar to traditional silicone. However, fluorosilicone offers improved fuel and mineral oil resistance, but poor hot air resistance when compared with silicone. Because of the strong low temperature performance, fluorosilicone O-rings are used commonly in aircraft components. Fluorosilicone offers heat resistance up to 350 degrees Fahrenheit and cold flexibility down to approximately minus 100 degrees Fahrenheit. Fluorosilicone offers strong chemical resistance for the following: aromatic mineral oils such as IRM 903 oil and fuels, and low molecular weight aromatic hydrocarbons. The bottom line is that fluorosilicone is a fluorinated version of traditional silicone. Fluorosilicone was developed as an aerospace material for handling fuel at extremely low temperatures. Broader industrial applications have developed over the years. Like silicone, it offers poor mechanical properties and should be avoided for dynamic applications. And finally, we will discuss polyacrylate, or ACM, which has good resistance to mineral oil, oxygen, and ozone. Water compatibility and cold flexibility of polyacrylate are significantly worse than nitrile, but it has stronger high temperature performance compared to nitrile. This material is used extensively within the automotive industry. Polyacrylate offers heat resistance up to approximately 350 degrees Fahrenheit and cold flexibility down to approximately -5 degrees Fahrenheit. Polyacrylate has strong chemical resistance to the following: mineral oil, such as engine, gearbox, and ATF oil, ozone, weather, and aging. Polyacrylate is not compatible with the following: glycol-based brake fluid, such as DOT3 and 4, aromatic and chlorinated hydrocarbons, hot water, steam, acids, alkalis, and amines. The bottom line is that polyacrylate is similar in chemical composition to NBR. It is used extensively in automotive engine and transmission applications and has higher temperature performance than nitrile with similar levels of chemical resistance. Thank you for watching this video on O-ring elastomer basics and common elastomers used for O-rings. I hope you found the information valuable. Please stay tuned for additional O-ring videos. Thank you for your time.